This video is a brief review of reaction thermodynamics. This is a reaction profile or reaction diagram or energy diagram that you have seen already, and you already know that there are three parts to it. Part 1, state before the reaction, that shows energy of reactants. Part 2, which is reaction pathway, that shows how reactants are converted into products. And part 3, state after the reaction, that shows the energy of the products. You already know that part 2 is domain of study of reaction kinetics. Well, parts 1 and 3 are area of study of thermodynamics. So reaction thermodynamics is concerned only with initial and final states of the reaction. So now we can look at how thermodynamics would look at a hypothetical example of a reaction in which A moles of compound A react with B moles of compound B to give C moles of compound C and D moles of compound D. And of course that's an equilibrium reaction. Since thermodynamics is concerned only with initial and final states, one of the important concepts in thermodynamics is that of equilibrium constant. So for reaction like this, we can define an equilibrium constant, and equilibrium constant is multiple of concentration of products divided by multiple of concentration of reactants. And of course, number of moles are used as exponents. I'm sure you're all familiar with this expression. This is something that is covered extensively in a general chemistry course. From the equilibrium constant, one can determine the extent of the reaction. If equilibrium constant is large, that means that reaction proceeds almost to completion, or at least that equilibrium is to the right towards the products. On the other hand, if equilibrium constant is small, then it means that reaction may not proceed or proceeds barely at all, and equilibrium is to the left. So that in equilibrium mixture, mainly we have starting materials, reactants, and very little products. Another important concept, thermodynamic concept, is that of free energy. And the reason why chemical reaction or any other physical process is spontaneous is that it proceeds with change, specifically a decrease in free energy. Now, free energy is defined as energy content of the system. And in this case, in case of chemical reaction, system are molecules of the reactants, and that may include also the solvent. So free energy is measure of potential energy of molecules or total potential energy of the system. Change in free energy is the difference in free energy of products and reactants. So what we are really concerned with is change in free energy. And from the change in free energy, we can determine whether process is spontaneous or not. Now, change in free energy is related to equilibrium constant. And as you have seen above, we can determine equilibrium constant experimentally from the concentrations of the species at equilibrium. So change in free energy, delta G, this degree sign in superscript indicates standard conditions. So change in free energy is minus RT ln K, K equilibrium. So R is ideal gas constant, T is reaction temperature, and ln natural logarithm of the equilibrium constant. So based on the change in free energy, reactions can be classified as exergonic when change in free energy is negative. So that's spontaneous reaction. Endergonic if change in free energy is positive. That would be a non-spontaneous process. Process that goes in opposite direction is spontaneous. And finally, if there is no change in free energy in the course of reaction, which is relatively rare, then process is thermoneutral. Don't confuse these concepts or mix them up with exothermic and endothermic, which are more commonly used. They refer to enthalpy, not change in enthalpy, not change in free energy. Here we are talking about change in free energy. And change in free energy tells us whether process is spontaneous or not. Change in enthalpy does not. So enthalpy is only one of the components of free energy. And in fact, that brings us to the expression for free energy that you can see from this equation that change in free energy equals change in enthalpy minus T delta S. So that's temperature, reaction temperature in Kelvins, absolute temperature, multiplied by change in entropy. So there are two components to free energy, enthalpy and entropy. And now we are going to look at the role of each of them in organic reactions. Enthalpy is a thermodynamic quantity that is related to the internal energy of the system. In case of chemical compounds, that means bond energy in a molecule. So that's the energy that is stored in chemical bonds. And it's the energy that either has to be put in to break the bond or is released when chemical bonds are formed. Bond energy convention is labeled as dH, and there is this degree sign to indicate standard conditions. And by convention, it's given as a positive sign, which means that bond energy is the amount of energy needed to break the bond. Of course, the same amount of energy is released when bond is formed. Here we can classify reactions based on or with respect to enthalpy as exothermic when change in enthalpy is negative. That means basically when heat leaves the system, so when heat is liberated, or endothermic when change in enthalpy is positive, when heat is taken away from the environment. We can look at examine the reaction of ethane and hydrogen bromide as an example of calculation of changes in enthalpy in the course of a chemical reaction. So we can see that in this case, some bonds are broken and some are left unchanged. To simplify the process, we ignore bonds that are not broken in the course of reaction. So there are 4 carbon-hydrogen bonds that are not broken, that appear both in the starting material in ethene and in the product, bromoethane. We assume that their energies are the same. They're not actually exactly the same, but they're close enough that we can ignore that difference. A little bit larger approximation is made in assuming that carbon-carbon sigma bond is the same strength in ethene and in bromoethane. That's actually not the case. Carbon-carbon sigma bond made from 2 sp2 hybridized carbons is noticeably stronger, but again, we ignore that. Again, the calculation error that we make is relatively small, and there is considerable simplification by doing it. So we are only considering bonds that are broken and bonds that are formed. And so the overall change in enthalpy will be the energy that has to be put in to break the bonds, the difference between energy that has to be put in to break the bonds and the energy that is released because of the bond formation. So we can see that carbon-carbon pi bond is broken in the course of reaction, and that requires 61 kilocalories per mole. Also, hydrogen-bromine bond is broken. That requires 87 kilocalories per mole. So the amount of energy that has to be put into the system for this reaction to occur, or bonds to be broken, is total of 148 kilocalories per mole. The amount of energy that is released, so that would appear with negative sign, is due to bonds that are being formed. As bonds are formed, energy is released. So carbon-hydrogen bond is formed, and formation of carbon-hydrogen bond releases 101 kilocalories per mole. Carbon-bromine bond is also formed, and formation of that bond releases 69 kilocalories per mole, for total 170 kilocalories per mole. And so when we subtract 148 minus 170, we end up with minus 22 kilocalories per mole. We can see that delta H is negative, and actually by a rather large amount, so this reaction is highly exothermic. So in this case, change in enthalpy will contribute to the process being spontaneous. It still may not be spontaneous because we have to look at the other quantity, entropy, but change in enthalpy is favorable. The other component of free energy is entropy. That's degree of randomness of the system. We often say this is degree of disorder of the system, not quite accurate, but it's degree of randomness, how many different states system can assume. We will examine role of entropy on isomerization of 2-butene. So 2-butene exists in 2 forms, cis and trans. So those are 2 isomers, those are 2 stable compounds. They are stable under ordinary conditions, but if they are heated, they can undergo isomerization reaction. So one isomer could be converted into the other. Line formulas are given underneath, and these molecules are planar because double bond is planar, trigonal planar. So trans isomer of 2-butene is more stable than cis isomer. Difference in energy is 0.6 kilocalories per mole. And the reason why it is more stable is that, as you can see in cis isomer, two metal groups are on the same side. Since molecule is planar, these two groups eclipse each other. So there is some steric hindrance. One would expect that if we were to carry out isomerization reaction, then only trans more stable isomer, trans butene, would be the product. But that's actually not the case. And the reason why that is not the case is that mixture has higher entropy compared to a pure compound. It has greater disorder. It can assume more states. So formation of a mixture is thermodynamically favored. So if we heat either cis or trans 2-butene to 400 degrees Celsius, that will cause pi bond to break. The intermediate shown in the middle is biradical. Biradical means two radicals. So each of the carbons is radical. And it has only sigma bond, so rotation is free. Of course, pi bond, when pi bond is present, it prevents rotation about carbon-carbon bond. But if there's only sigma bond present, rotation is free. That's, of course, a short-lived intermediate, and biradical very quickly reforms double bond to form one of the isomers. Regardless of whether we start with cis or trans isomer, we end up with same mixture. It contains 39% cis and 61% trans isomer. The reason for it, again, is that a mixture has higher entropy, and so for that reason, formation of mixture is preferred. On the other hand, since trans compound is more stable, trans compound is predominant component in the mixture. So while mixture is formed, organic reactions have tendency to form mixtures, more stable compound, because of the enthalpy factor, predominates in the mixture. So that's how both factors, enthalpy and entropy, contribute to change in free energy. So reaction is going to be spontaneous. You can see from this equation delta G equals delta H minus T delta S. Reaction is going to be spontaneous if change in enthalpy is negative and change in entropy is positive. If entropy increases in the course of process because there is minus sign before entropy. Note that entropy is multiplied by absolute temperature. So if changes in enthalpy and entropy are both negative or both positive, then it may depend on relative magnitude of temperature whether the process is going to be spontaneous or not. So if both are positive, both change in enthalpy and entropy are positive, positive change in entropy contributes to process being spontaneous. That means at high temperature, T delta S factor will be large, and therefore overall process will probably be spontaneous. On the other hand, if both are negative, delta H and delta S are negative, then change in entropy does not makes process not spontaneous, while change in enthalpy favors the process. So then at low temperature, T delta S factor will be relatively small and process will be spontaneous. Of course, if delta H is positive and delta S negative, then that process cannot be spontaneous. We can still make it spontaneous by coupling it with another spontaneous process to make the overall process spontaneous. So this brief overview hopefully helps you understand the role of enthalpy and entropy in organic reactions. One other important factor is that typically delta H factor, unless temperature is relatively high, delta H factor is much larger than T delta S. And frequently we can ignore change in entropy in organic reaction and only consider change in enthalpy. But that's not always the case. And specifically, it's not the case in elimination reactions. So this completes our review of reaction thermodynamics. And next we are going to look at reaction mechanism and reaction control.